Hello all, I hope your online learning is going well with all of your courses. I want to pick up today where I left off yesterday, which is looking at Newton's three laws of motion, which look at the relationship between forces and the motion of an object. And as we were talking about yesterday, if we know kinematics data, we can analyze the motion of the object, and the link between unit 1 and unit 2 is acceleration. So acceleration here is just going to keep popping up all the way through this unit because it is the link between the motion of the object and why the motion is doing what it's doing. In other words, what are the forces doing to that object? Now, yesterday we started with 4.1, which is Newton's law of motion or the law of inertia. Okay, Newton's first law basically says an object will maintain its state of motion unless acted upon by some external unbalanced force. In other words, the unbalanced force is the sum of the forces. If the sum of the forces is zero, then there is no unbalanced forces. The forces are balanced, and the object will not respond, it will not accelerate if there are no unbalanced forces. Right? So long as the forces cancel out, right, and there is no unbalanced force, the object will not accelerate. As soon as there is an unbalanced force now, the object will accelerate. So if we move into 4.2, I want to look at the relationship now between the force that's applied to an object and its acceleration. Again, remember, acceleration fits into all of those equations. Delta D equals V1 delta T plus acceleration delta T squared. Right? Delta D equals V2 squared minus V1 squared over 2 times acceleration. So the acceleration that we've been talking about all the way through the first couple of months, first month or so anyway, of this course, all comes back to why it's accelerating, which is the forces that are acting on it. Now, if from the first law, it says if an object has no unbalanced forces, then it will not accelerate. In other words, if F net equals 0, acceleration will be 0. Second law says if the F net is not 0, then the object will accelerate. Right? If the F net is not 0. In other words, as soon as I apply an unbalanced force to an object, it's going to respond by changing its velocity, right? Which is what acceleration is, change of velocity over time. Now, logically, think about kicking a ball that's on your front lawn, right? The direction for the acceleration of the ball will be the same as the direction of the force that's applied to the ball. All right, so the direction for the acceleration will be the same as the direction for the net force. Okay, so all of these are really fundamental to our understanding of Newton's second law. And then this continues on and says, okay, this again should be common sense. The harder you kick the ball, the faster it's going to leave your foot. In other words, the more will be its acceleration. So there is a relationship between the amount of unbalanced force applied to an object and its rate of acceleration. Right? The little proportionality statement, proportionality symbol here is basically telling me that if I double F net, I will double A. If I have 10 times the amount of unbalanced force, I will have 10 times the acceleration. Right? It's a direct proportionality. Now, that's assuming that the mass of the object that we're applying the force to is constant. I'm kicking the same ball. Twice as hard, it's going to have twice the acceleration. What about if I apply the same amount of force to different objects that have different masses? Again, think about kicking an object with a light mass with a certain amount of force. It will maybe, if I give it a good hard kick, it will go quite far. If I increase the mass of the object, say from 1 kilogram to 100 kilograms, and I apply the same amount of force to it with my foot, might break my foot, the acceleration is going to be very small for that object. As m goes up, acceleration is going to go down. It's an inverse relationship. All right, so for constant F net, the magnitude of A is inversely proportional to m. Right? A is related to 1 over m. Right? And now, if I know that A is proportional to F net, and A is also proportional to 1 over M, then A must be proportional to F net over M. If I rearrange this equation to take the mass from the denominator up beside A here, I end up with F net is proportional to M times A, or MA is proportional to F net. And then to get rid of that proportionality symbol here, right, I need to put a constant in. Right, the constant turns the proportionality into a direct linear relationship here. The constant becomes K, and the K that we're going to use for this is going to be a K value which is always equal to 1, okay, under one set of criteria. K will always be equal to 1 so long as the mass is in kilograms, and the acceleration is in meters per second squared. If that is the case, then K will be 1. And the units here have to work so that the units that I'm left with for F net here, which we've been using units of newtons, named after Sir Isaac, F net is measured in newtons, where M is in kilograms and A is in meters per second squared. So if I quickly look, I'm just going to try this for a minute here. See if I can find the workspace. Okay, so if F net equals K times M times A, and F net is in newtons, and M is in kilograms, and A is in meters per second squared. How do I get newtons over here? Well, K must be in units that are in newtons per kilogram meter per second squared. Okay, squared. And what that does then, if K is equal to 1 Newton per kilogram meter per second squared, notice that the kilograms will cancel, the meters per second squared will cancel, and that my answer will be in newtons. That's only because I have this really arbitrary and bizarre value for K, which allows me to convert the relationship that exists between mass and acceleration into a unit which is an arbitrary unit. Remember, this is based on fundamental units, right? Mass, the amount of matter present in an object, right? Meters, a fundamental distance, right? Seconds, a fundamental unit of time. Newtons, oh, some guy's name, right? So I've got to find a way to take my fundamental units on this side and allow them to become something that I can talk about when I'm talking forces, and I can talk about by the end of this next week or so, you'll be understanding how much force is 10 newtons of force, how much force is 100 newtons of force, how much force is 1,000 newtons of force, right? So we're going to understand forces in newtons, and this will all work out. Okay, I'm just going to try and keep myself, oops, cancel. I want to cancel. I want to try and keep this space clear so I can use it for solving problems in a minute. Okay, so let's go back to our short note for 4.2. I'm almost done it already. Okay, so what does this K value mean? The K value says I can now define how much force a Newton is. Right? 1 Newton is defined now as the amount of force that's required to accelerate a 1 kilogram object at a rate of 1 meter per second squared. Right? Given the definition that we had a moment ago, right? 1 Newton is the amount of force required to accelerate 1 kilogram of matter at 1 meter per second squared. F net equals ma. That's Newton's second law. All right, so now if we look back to the homework that I had assigned for this section, questions 19 to 32, this is one of the questions that I'd answered in the discussion forum. Again, I'm hoping that if you get stuck on questions, definitely turn to that discussion forum, because I always like to take up some questions in the homework. So I'm going to do these differently starting in the next day or so. I've got a new webcam that I've ordered, and it's going to help me to do these here at home on my whiteboard. But for now, I'm going to do it on this page here. So if I scoot down, I've got a free page down here. I'm going to erase it. Now, if I look at question number 19, which is the first question in the homework, question 19 is asking me to calculate the net force acting on a 20 kilogram object if it's accelerating at a certain rate of acceleration. Right? So if I look at a 20 kilogram object that's in free fall, we know that free fall for objects indicates it's going to have an acceleration of 9.8 meters per second squared. So why is my 20 kilogram object? Imagine holding a cement block in front of yourself that's 20 kilograms and then letting it go. What's it going to do? It's going to fall. Why is it falling? Because there's a force pulling it down, which is gravity. Are there any other forces acting on it? No. At this point in time, it's falling and the planet is pulling on it. Right? So F net here, right, the net force is going to be equal to the mass times the acceleration. So if I go back to my blank page here, okay, so for question 19a, right, I've got my unknown says calculate the net force. F net is unknown. Acting on a 20 kilogram object that's accelerating at 9.8 meters per second squared down. Now, it doesn't say that actually. Let's get rid of the down, because it could be accelerating any direction. I would say almost for sure it's down, because of the fact that it's 9.8 meters per second squared. But we'll just say, okay, it's accelerating. So there's my given information. My required to find, I've already got that, is F net. My approach is going to be F net equals ma. Right. My substitution in gives me an F net, which is equal to 20 kilograms times 9.8 meters per second squared, which is 196 newtons. Two significant digits makes it 2.0 times 10 to the power of 2 newtons. Right? And then my phrase, therefore, the net force is 2.0 times 10 to the 2 newtons. All right, so there's the question 19a. Question 19c is asking you to do a similar thing, except now, come on you, now the units are a bit interesting. All right, so the units are in kilograms, meters per hour, sorry, I got no easy way to clear my board here. Maybe I can just move up. There we go. Okay, so let's, for 19C, saying calculate F net if we have a 20 kilogram object. So the given here is the mass of 20 kilograms, having an acceleration of 5.669 kilometers per hour squared. Bizarre units. I've never seen that unit used before, and you probably never will again. They're just trying to make your life difficult as a student in 3U physics. So we know my acceleration has to be in kilometers per second squared. So I've got to convert my kilometers into meters and my hours and hours down here into seconds. So remember, hours squared is hours times hours. So I'm going to convert my kilometers because I know that 1,000 meters, come on, is the same as a kilometer. And my kilometers bottom and top cancel. And I know that 1 hour is 3,600 seconds, or 60 times 60. Oh, but I've got hours squared, so I'm actually going to have to take this whole thing and square it. So now I have hours squared on top and 3,600 squared on the bottom. Now, if I do my math, let me get my calculator out here while I'm sitting here. I've got 5.669 times 1,000 divided by 3,600 squared, and I'm getting 4.374 times 10 to the power of negative 4. Notice that my hours and hours have canceled, my hours and hours have canceled, and I'm left with meters over seconds squared. So meters per second squared. So there's my given information, and my required to find is F net. And I'm going to solve this with my one formula for Newton's second law, F net equals ma. The nice thing about this unit, there's really only one new formula for most of the unit, if not the whole unit, which is F net equals ma. I'm just having a look here. We're going to get into friction in the next unit, and then we'll have a couple of more. But for now, we're just going to have F net equals ma. So if I substitute my numbers in, F net is equal to 20 kilograms times 4.374 times 10 to the negative 4 meters per second squared. I should double check that math here one more time before I make everybody crazy with the wrong number. Yep. And I'm going to take that number times 20, and I will get an F net, which is equal to 8.7 times 10 to the power of negative 3. So my phrase, therefore, the net force is 8.7 times 10 to the power of negative 3. Ultimately, you would want to say that it's in the direction of the acceleration. Okay, but we're not going to worry about that for now. Right, and then you're going up to 32. So question 26 I did on in the homework the other day, but if I go back and let's just look at 26 again. So 26 says the supertanker has a mass of 1.0 times 10 to the 8th kilograms. So given mass is 1.0 times 10 to the 8th kilograms. I've got a new stylus coming too. It tells me that it reaches a speed of 4.1 kilometers per hour from rest after it's traveled 3.5 kilometers. What is the magnitude of the unbalanced force acting on the object? Oh, so I need to find, before I can find what is the magnitude of the unbalanced force. So the question's asking me for F net. And I know to find F net, I need to know M and A. I know M, but I don't know A yet, so I'm going to have to solve for A. So to solve for A, I'm going to use my kinematics data. I know the delta D is 3.5 kilometers, or 3,500 meters. I know that V1 is from rest, and V2 is 4.1 kilometers per hour. I convert that to meters per second. I know that 1 hour is 3,600 seconds, and that 1,000 meters is a kilometer. So I take my 4.1 times 1,000 divided by 3,600, and I get 1.14 meters per second. Okay, if I know delta D, V1, and V2, I can solve for my acceleration using my formula delta D equals V2 squared minus V1 squared over 2A. And let's rearrange to solve for A. A equals V2 squared minus V1 squared over 2 delta D's. And then if I substitute in my numbers, my acceleration is 1.14 V2 squared minus V1 squared divided by twice my distance. And I'm getting 1.85 times 10 to the negative 4 meters per second squared. And now I can go back and I can solve for F net here using MA because I know the mass. Oops, I know the mass and I know my new acceleration. Okay, so I can actually go in and solve for F net. MA, which equals 1.0 times 10 to the 8th kilograms, times my 1.85 times 10 to the negative 4 meters per second squared. And I'm going to get 1.9 times 10 to the power of 4. Notice I've only got 2 sig digs because of the numbers in the question. 1.0 times 10 to the 4 kilograms, 1.8 kilograms, 3.5 kilometers, 4.1 kilometers per hour. So my answer should have 2 sig digs. All right, so my phrase now, therefore the F net is 1.9 times 10 to the power of 4 newtons. Okay, so like I said, I really like Newton's second law. I find it's very straightforward. It's just F equals ma, F equals ma, F equals ma. We may need to still be using some of the tools from chapters 1 and